Last time we were working on section 8.1, more applications of integration. In this case, we did the application to finding the length of the arc, or arc length, most commonly known. This time we're going to apply actually integration to find the surface area. Well, here is the formula. I'm going to give you the formula here. Although I'm not going to derive it like very thoroughly, just the same way we did it last time, or last week rather, with the arc length. But we are going to do some mini derivation here and there. So this is what we're going to get. So essentially, we have a function f of x, but this function, this length, gets rotated. And yes, it's originating a solid, if you will. It's originating a solid. However, we are not finding the volume the same way we did it at the beginning of the semester. We're finding the area of the surface. In other words, in a way, we're finding like the skin of the solid in terms of area, if you will. All right, so here's a couple of things. So notice this formula has an r of x. And well, this formula is very similar to that of the arc length. Let me write down the formula for arc length. That's a little s, I believe it was. Oh, no, it was L. That's the integral from a to b, square root of 1 plus f prime squared with respect to x. Well, this formula for surface area is similar in the sense that we, number one, have this 1 plus f prime squared dx. It's coming back, but in this case, what extras do we have? We have this r of x that we didn't have before in the arc length formula, and we have this 2 pi. Well, where is that 2 pi coming from, and where is that r of x coming from? Well, so again, backtracking to calc 1, when we found the area under the curve, we added infinitely many areas under rectangles, right? That was using Riemann sum. And then last week when we defined the arc length, we did something similar. But in this case we didn't add infinitely many areas under a curve, but rather we added infinitely many lengths of curves. So in this case we are going to get the surface area. Check this out. Check the approach. So we're going to find this surface area of what we call a frustum of a cone. All right, so what is that? Frustum of a cone. Or another way to say this, a truncated cone, if you will. So it's a cone that we just chop that cusp, so that's pretty much what it is. But the thing here is, okay, let me draw the picture below again. So this have an r, let's call this r1, that's the smaller radius, and here is the larger radius. For the sake of simplicity, we're just going to find the average of those two radii. So in general, to find the area for the surface area for this truncated cone, that's 2 pi RL. All right, where R is the average between R1 and R2. And well, this L will be that's length, or rather me use that's length distance along the edges of the cone, which ultimately, coming back to this picture, well, because this is going to be a sideways truncated cone, this little L will really be that L from the arc length that we are rotating, and this is where this square root of 1 plus f prime of x, quantity square, is being here again. So in this case, well, what are we going to do? So this will be in our setting here, this will be 2 pi r of x times delta L, where delta L, that's an increment, just an increment in our length. Let's call this more properly delta L. It's just an increment, or the partition, if you will, for the arc length. But we know what delta L is from the previous section. R of x, that's the square root of 1 plus f prime squared. But because this is involving an increment, a change, that's the d, well, let's call it dx, all right? Because, well, to go from this point to that point, that requires a dx. You know, it's a differential, it's a small increment. So, well, adding infinitely many of those, what are we going to get? 2 pi, 2 pi, the integral from a to b, the radius times the radical 1 plus f prime of x squared with respect to x, which is the formula that we have above. Question?
Why are we using y's in the formula?
Which one? Right here?
Yes.
Oh, so this second formula that we have here, that's when we use functions of y, which will be the case that we use, by the way. However, there's a silly typo here. Whenever we define functions in the y direction, we integrate from c to d. All right, that was my little issue here. All right, but other than that, that's the same. So here is where this surface area is coming from. Okay, let me give you more pictures about this. Well, so on the next page, so what do we have? So whenever we have functions of x, so this is where we always need to do a small picture so we can easily, or so we don't make a mistake when defining that r of x, whether it's f of x or just x. So, for example, let's consider functions of x about the x-axis. Well, rotation about the x-axis, which is this setting here. Well, so what are we going to have? This function, whatever it is, it could be a curve, it could be even a horizontal line, whatever function is. So in this case, this radius, that radius that we define in the general definition here, this r of x, can play either one or another role. It could be the function f of x or just x. Well, what is that going to depend on? Well, it will depend on what we obtain. So for example, we're rotating about the x-axis. So the distance from the axis of revolution to any point on the graph, do you notice how that distance is vertical? Well, because that's a vertical distance that's described by a y. But in this case, that y could represent either the function, well, in this case for the height of the function, in this case this is the function, or on the other hand, if we rotate this same graph about the y-axis, but we're still using functions of x, well, that radius, that r, is the distance from the axis of revolution to any point on the graph of the function f of x. So that's one distance. That could be another distance if you want, or even how about this distance? You know, there's many possibilities, but the thing here is that distance, do you notice how it's horizontal? Well, so that's just defined by x. Alright, and in that case, well, when it's being rotated about the y-axis, this r of x, again, it's either f of x or simply x. And the reason why we don't change to anything other than x is because we want an integral in terms of x. So, later we're going to look at a different setting. However, if we were working otherwise with functions of y, this x would have been g of y. But well, that's described below here. When using functions of y, rotation about the same axis as the functions that we want, that r of x, or I mean r of y, it's the function itself. But if in this case we're rotating, we're using functions of y but rotating about the x-axis, that's going to be just y. Actually, don't worry about too much like trying to memorize all these 4 settings. Actually, we will get to see that as we go through the different examples. We're going to do one example of each at least, and you'll see how we're going to set it up. Question?
So on the previous page, you mentioned that if it's going around the y-axis, then you do it in terms of y.
Mm-hmm.
Related to this one.
To this one right here?
Yeah, because now it's saying that if it's around the y-axis, it's from a to b of 2 pi x, and the rest of it. It looks like it's
Oh, I changed the limit here, so I had a typo here. It's supposed to be from C to D. Yeah, that was a little typo. So let's have a look at one example here. So number 1, we have the curve y equals the square root of 4 minus x squared from -1 to 1. Notice in this case they're giving us the limits. We don't have to figure out anything. And this square root of 4 minus x squared actually represents part of the arc of the circle x squared plus y squared equals 4. Number 1, how does that circle look like? What are the properties of that circle? It's centered at the origin, and what else? It's a radius too, right? So that means that if we wanted to draw the whole graph, it would have looked like this. And notice in this case it's only the upper semicircle. And that's because, well, our radical function has the positive sign, because if you try to solve for y on the given equation, x squared plus y squared equals to 4, try to solve for y, you would get 2 different solutions, plus or minus in this case because of the square root property. But in this case, because they're just giving us explicitly the positive radical, well, in this case it's just the upper semicircle. However, that's not the portion of graph that we want. Notice they're asking us to find the area between -1 and 1, not between -2 and 2. So that's not going to be the graph either. So it's only going to be this. Alright? Well, so number 1, let's write down the formula in general. Notice in this case, we have functions of x, we have limits in the world of x, and they're asking us to find the surface area by rotating about the x-axis. So number 1, let's write down the 2 pi integral from a to b of r of x square root of 1 plus f prime squared dx. Alright, let's do the rotation about the x-axis. So what is this going to give us? Number 1, well, this portion of arc length is going to look like this. So number 1, number 2. Alright, it's going to look like this. So what's the shape of this solid in this case? So we're getting a solid that is flat on the side and kind of circle about the direction of rotation. To have a better picture of this, have you seen those big Parmesan cheeses? The ones they import from Italy, you know, not you know, those you get, you know, you get like a, I don't know, 100 grams at the market, but they actually pieces of these big discs, right? They're flat from the top and the bottom, but they're circular from the side, from the edge of the sides. Well, so that's essentially what we're finding the surface area of. All right, now notice the rotation is about the x-axis. That means rather that the distance from the axis of revolution to any point on the edge of the function that we're rotating it's vertical. Isn't that the same as saying y? Yes? Alright, so that means y. But in this case, okay, we have a y, but we are working with functions of x. Lucky for us, we're going to replace this. We have that function of x, which is going to be f of x. Well, so let's write down the integral. Also, well, notice the formula calls for the first derivative of the function. So let's, number one, find that derivative. So this is the first thing we do here is write y equals to 4 minus x squared to the 1/2. And let's take the derivative, y prime 1/2 4 minus x squared to the negative 1/2. Using chain rule, then we need to multiply by the derivative of the inside part of it, right? What's the derivative of that? Negative 2x, all right? Oh, so what do we do then? So let's, okay, my advice, simplify as much as you can, because when we get to put these derivatives on the integral, the expression is going to get really, really nasty, and you don't want to deal with negative exponents and negative rational exponents. So that's my advice. All right. Oh, wait a minute, not that one. All right. This means so that's going to be x. So y prime equals to x over 4 minus x squared to the 1/2, which is the same as x over the square root of 4 minus x squared. Alright? Oh, actually minus. That minus doesn't get cancelled. Alright? So let's put this and let's get ready to work with the madness here. Alright? So, well, it's not going to be as bad as it looks. You'll see. So number one, this is 2 pi integral from -1 to 1 of r of x, which is f of x, which is actually this function f of x. It's a function of y. So that's the square root of 4 minus x squared times the square root of 1 plus the derivative negative x over the square root of 4 minus x squared, quantity squared, with respect x. And don't even attempt use substitution here. So instead, we will simplify the integrand first, and then don't worry, this is going to reduce really, really nicely. You'll see. All right, so number one, let's square numerator and denominator of the derivative square. So how about 2 pi integral from -1 to 1, and that's the square root of 4 minus x squared times the square root of 1 plus x squared over 4 minus x squared. And where did I get this 4 minus x squared from? Because I'm squaring this radical. The radical cancels the square. So there's a couple of things we can do here. Number one, we can take the approach that we did last time about finding common denominators, simplify everything inside of the radical, and then multiply with the other radical. I'm going to take a different approach this time. So I'm going to use one of the properties of radical, the one that says the square root of a times the square root of b is the same as the square root of a and b. In other words, when you have a product of two radicals, you can write it as the radical of that product. How is it going to work for this? Well, number one, that's the integral of 2 pi integral from -1 to 1. That's the square root of 4 minus x squared times 1 plus x squared over 4 minus x squared with respect x. All right. So what am I going to do here next? So I'm going to distribute 4 minus x squared times 1 and 4 minus x squared times x squared over 4 minus x squared. This, so you can see how these are going to simplify. Well, I'm going to write the whole thing. I'm going to write it here. That's 2 pi integral from -1 to 1. That's 4 minus x squared times 1 is 4 minus x squared plus 4 minus x squared times x squared over 4 minus x squared, everything underneath the radical, and see how this cancel out, leaving us with 2 pi integral from -1 to 1 of the square root of 4 minus x squared, plus the only term that survives the cancellation on the second term is the x squared. And notice again how these two x squareds cancel out, leaving us with 2 pi integral from -1 to 1 of the square root of 4. And what's the square root of 4? Okay, that's a 2 times the 2 pi outside. Isn't that going to be a 4 pi? Okay, another thing I would like to discuss, because this same thing I'm going to do it in the next exercise. Notice the symmetry of the picture here, not the symmetry of the region that we are rotating. It would be the same integrating from -1 to 1, then integrating from 0 to 1, as long as we multiply by 2. Because technically we are finding the area from 0 to 1, and then from here multiply by 2, because it's the same area from on one side or the other side. And well, it's important to use these symmetry properties to save a lot of work. Trust me, we're going to use it in the next example to save a lot of work. So that's 8 pi integral of the x. So what's the integral of the x? Just x from 0 to 1. So that's 8 pi 1 minus 0, 8 pi. All right. So that is our first exercise on finding the area, the surface area for a given function at a given, about a given axis of rotation. Question?
Wait, how did you get 2 times 4 pi?
Multiplying. So I'm integrating instead from 0 to 1, and then multiply by 2 to get the whole surface area. All right. Let's look at the next example. Yes.
So, when you multiply 4 minus x squared times 1 plus x squared over 4 minus x squared, how come you didn't have to use FOIL? It should be distributed.
Well, no, because if we do the FOIL here, I mean, we would have to factor it out back again, so we can cancel this instead. So, well, essentially, I'm using, number one, I'm using the distributive property here inside of the radical to multiply 4 minus x squared times 1, which is 4 minus x squared. And then 4 minus x squared times x squared over 4 minus x squared. This 4 minus x squared, actually, let me highlight it. This one, and this one. And instead of keep foiling, well, just simplify these two, because essentially there's invisible parentheses there, they're common factors, we can divide out those common factors, right?
Why did we change the bounds from -1 to 1 to 0 to 1?
So typically there's issues with limits of integration that are negative, especially when the lower limit is a negative. Typically there's issues with subtracting a negative or forgetting one of those negatives. To avoid those little issues, what I do instead is integrating from 0 to 1. And actually another advantage of using the symmetry property is that, well, when we plug in a 0, typically that zeroes out a whole term. But this trick, well, it's really not a trick, it's actually properties. It only works when you know for sure that the region that you're integrating over is perfectly symmetric. If you have it somewhere else, no, we can use that anymore. Right? Let's see, let's look at question?
I still don't understand why you didn't use FOIL.
Because to cancel this, like this.
Well, why is it not 4 distributed to all of that, and then minus the x squared distributed to the entire parentheses?
So, okay, so this quantity.
Can you distribute an entire binomial by itself?
Yes, you can do, or even a trinomial, or many, for example, times 1. For example, if I have a plus b times c plus d. So the first thing we would think of is doing FOIL, right, for multiplications. But another thing we could do instead is to treat this AB as one single factor and multiply with the C to give us an A plus B times C, plus treat this like one single and then multiplying with the D here, which would be A plus B times D. And then once we do that, we can further distribute, which is the equivalent of doing foiling. All right, so you can, so yeah, if your question is, can we treat an expression with more than one term as one single factor? Yes, that's correct. All right, let's look at the next example. So example number 2 is to repeat exercise 1 but rotating the region about the y-axis. All right, so it would be great if we first we draw a picture of what we want to integrate over. So, and well, so that's going to be again that portion of circle of the length of a circle that goes from -1 to 1. However, this time we're not going to rotate about the x-axis to get that Parmesan cheese. This time we're going to rotate about the y-axis to get the solid essentially. So what are we getting in this case? So we're getting like a cylinder with a flat bottom, and the top is kind of spheric. It's a spherical top. All right, so let's write down the formula for surface area. That's 2 pi times the integral from a to b r of x times the square root of 1 plus f prime of x, quantity squared, with respect x. Okay, so now let's figure out what r of x is going to be. And r of x, again, it's the radius of the solid that we're rotating, and that radius goes from the axis of revolution to any point in the direction of the rotation in this case. Now observe that radius. Is that vertical or horizontal this time? It's horizontal. And well, which variable do we use to relate horizontal distances? X, right? So r equals to x. Well, we don't need to change that x to g of y, because we're not working with functions of y. If we were, if the problem said work it with functions of y, then we would have to change that to a function of y, but it's not the case. Don't worry, we're going to do one of those later, right? So let's see. 2 pi integral from -1 to 1 x square root of 1 plus the derivative that we already got in the previous problem, -x over the square root of x, 4 minus x squared. Oh, come on. Quantity squared with respect x. Okay? Again, remember that thing about symmetry I did once I finished the integral? Well, it turns out that taking advantage of that symmetry of the region, you can do it at any time. And I'm going to do it right now. Well, first I'm going to simplify the integral a little bit from something to 1 first, and then that's x times the square root of 1 plus x squared over radical squared. That's oh, I'm not gonna have enough space, never mind, I'm gonna use it here. So this will be 2 pi integral from something to 1 x root of 1. I'm gonna leave a space for something, you'll see. And negative x quantity squared, again, that's x squared over radical quantity squared. We're just left with the quantity underneath this little radical. Well, so we want to simplify the quantity inside of the parentheses. This time we're going to do the long method, not like distributing that we did before, because this x itself is not going to cancel out 4 minus x in the denominator the same way we did it. So, well, this one is the same as saying 1 over 1, and if we find an LCD, then we would need to multiply that 1 over 1 by the missing factor so that we get a common denominator. And that missing factor is 4 minus x squared. Then we can combine these fractions together. Now about the limits of integration. So we can either integrate from -1 to 1, or we can integrate from 0 to 1 provided we multiply by 2. Alright, that's again taking advantage of the symmetry, and in this case you might want to do it because, well, you'll see why. So let's combine this together. That's 4 pi, the integral from 0 to 1 of x times the square root of 4 minus x squared plus x squared divided by 4 minus x squared dx. And yes, well, this madness looks crazy. However, see how a lot of terms get cancelled, or some of the terms, not a lot of them. Well, so what can we do from here? So we're going to be left with 4 pi integral from 0 to 1 of x square root of 4, which is the only term that survives in the numerator, divided by 4 minus x squared with respect to x. What can we do at this point? Number one, I'm going to use another property of radicals. That property that tells us that whenever we have a radical of a quotient a and b, we can write this as the quotient of two radicals, which is what I'm going to do here. And that's so we can simplify the square root of 4, which in this case is just going to be 2. And that 2 multiplying with the 4 pi, that's going to give us 8 pi. Integral from 0 to 1 of x, and that's 1 over the square root of 4 minus x squared dx. And it would be better if we write this x on top, so we can easily see which method of integration we would be using. Any ideas on which method? Use substitution. This is a great candidate for use substitution because the degree inside of the radical, which will be RU, is 2. Take the derivative of that, is 1 degree less, and we check that. We have that x multiplying with the dx, so it should work. Let me do that use substitution. U equals 4 minus x squared. Du equals negative 2x dx, and x dx negative 1/2 du. And again, in this case, notice how we have a definite integral. So if we are carrying the problem to integrate it in the world of u, we also have to carry the limits to the world of u. And I highly recommend you do this because we have radicals. You don't want to back substitute to have a bunch of radicals, and then on top of that having to do a bunch of arithmetics within 2 radicals in it. So that all that work is going to get simplified by changing the limit. So u of lower limit, which is 0, and u of 1, which is upper limit. So that's going to be 4 minus 0 squared and 4 minus 1 squared. That's going to be 4, that's going to be 3. And when we do the u substitution, this will become 8 pi integral from 4 to 3, And I know, don't freak out if your lower limit is larger than your upper limit. We're going to take advantage of a property, you'll see. And that's a negative 1/2 du over the square root of u. So suppose we integrate that function with upper limit being smaller than the larger limit. Potentially we would get a negative result. But do you see this negative? That's going to relieve that negative in the end. Or, well, number 1. So that's going to be 8 pi times negative 1/2. That's negative 4 pi integral from 4 to 3 of u to the negative 1/2 du. What am I doing here? Changing this radical to rational exponent and then moving it to the numerator with negative exponent so we can integrate it, because just like this we cannot integrate it. Okay, yes?
Negative effect?
But times 1/2, 8 pi times 1/2, so that reduces to 4 pi, negative 4 pi. Question?
Can you use another property that is very similar?
That was my next line here. Yep. So if this is still freaking you out about, well, why I don't like this negative and I don't like this lower limit being larger than the upper limit, it seems like I'm making the wrong work here. Well, you can always take advantage of this property. Whenever you have an integral of a function f of x dx, you can always reverse the limits of integration provided you change the sign of the integral. So that's the property that we are going to use in here. And notice we have a negative sign. We can use that negative sign to reverse the limits of integration. So how about we go about it? So that's a positive 4 pi integral instead of 4 to 3. That's from 3 to 4 u to the negative 1/2 du. And that's going to be u to the 1/2, well, 4 pi, u to the 1/2 divided by 1/2, evaluated from 3 to 4. Okay, what's dividing by 1/2? Isn't it the same as multiplication by 2? So 4 pi times 2, that's 8 pi times root of u from 3 to 4, and upper limit minus lower limit. Just simplify the root of 4, which is 2. Root of 3, just leave it as root of 3. So 8 pi 2 minus root of 3. Final answer. So another thing that we want to compare in this case, having the same region, even if you use, whether you use functions of x, functions of y, just changing the direction, the rotation changes the whole result. See how this result is different from the previous one, in which we rotated about the x-axis? Well, this cylinder with a spherical top is definitely not the same as that Parmesan cheese in the previous example. So two different shapes, we would expect two different results of surface area. All right?